Greetings. I welcome us back to another section of our class. And today we're going to be talking about Chem 172, which is also known as the chemistry practical. We want to look at the revision because of the ongoing examination. Okay. The next time I'm going to do this chemistry practical, I'm going to teach us some vital things we need to know. Then we'll now look at the past question as to uplift our spirit on what the examiners might want us to do. So first of all, I would like to define what is volumetric analysis. Volumetric analysis. Volumetric analysis. Now, you need to take down a lot of notes so that you can be able to follow up in the class. Let's start with this volumetric analysis. Let's write. I said, what you're going to do now, since you have gotten the volume to be this, what you're going to do now is to measure out 0.127 dm cube of this acid that you have at hand. Like I said, you are a student, you came to visit the school, and the man gave you this thing, and your sir gave you this and said, please help us and prepare 2 molar concentration on 1 dm cube of this solution. Then share it to each of the table. So what you are going to do is, first of all, you try and calculate the concentration of the acid given to you. You have gotten the concentration of the acid as 11.6 mol. Then you now calculate the volume of that acid you need by calculating using C1V1, and you have gotten the volume you need. So you get measuring cylinder or a burette, turn into a volumetric flask. So what you do is you measure out with a measuring cylinder, you measure out this volume and put it into a volumetric flask that is up to 1 dm cube. You know that 1 dm cube is 1000 cm cube. So 1 dm cube is bigger than this. Hope you see it. 1 dm. So maybe this is this thing. So if you measure out this, it might be here. But the total here is 1000 cm cube. That means if you reach here, it's one, maybe here is 0.17. Okay, 1000. Okay, let me say this is 1 dm cube. Okay, here now is 0.12 dm cube. You measure this thing out and pour it in from a measuring cylinder and you pour it here, and maybe this is where it is. Then you now use water to fill it up. Use water to fill it up till it gets to this mark. Use water to fill it up till it gets to this mark. This solution here now has this concentration. That's what we are trying to say. Then it is this solution now you start sharing to the whole tables. Do you get what we're trying to say? And that is why we are learning dilution formula and dilution law. There is no much about it. I believe this is well understood. Now again, let's look at one of the application in the exam. Question 2B, 2022/2023. Question number 2B has this question. It says, how will you prepare 2 molar concentration solution of H2SO4 acid if Sg is this, percentage composition is this, and you have this? Remember, we say first of all you are going to find the concentration in gram per dm cube. How do you find concentration in gram per dm cube? It's going to be, first of all, concentration in gram per dm cube. So it's going to be 92 over 100 times, this one now will be 1.84 times 1000. Remember that one was 1.18, okay? 1.84 times 1000. And that will give us 1840. So it's going to be times 1840 over 1. And that will give us, if you do that very well, 92 over 100 times 1840 gram over 1. That will give us 1692.8 gram of what? H2SO4. So it means this inside 1 dm cube. So therefore, concentration in gram per dm cube becomes 1692.8 gram per what? dm cube. I've gotten concentration in gram per dm cube. I've gotten my concentration now in gram per dm cube. The next thing I'm going to get is concentration in mole per dm cube. And we say concentration in mole per dm cube is equals to concentration in gram per dm cube over molar mass. You remember that? So our molar mass now for H2SO4 will now be, we are talking about H2SO4. This is 2 times 1 plus S is 32 plus 16 times 4. And that should give us a molar mass of that should give us 98 gram per mole. Okay, so concentration in mole per dm cube is equals to concentration in gram per dm cube, which is 1692.8 gram per dm cube over 98 gram per mole. And this will become, if you do that very well, you are going to be having 17.3 mole per dm cube. You have gotten the concentration of that solution you are having in your hand. In mole per dm cube, it is 17.3 mole per dm cube. The next you are going to get now is the volume you need to measure out in the measuring cylinder. The volume now. So for me to calculate the volume, remember I'm going to be using what we call C1 V1 equals to C2 V2. So let's see that. We have C1 V1 equals to C2 V2. Since the one you want to obtain is the 2 molar concentration, so it's going to be of V2. So my C1 becomes this 17.3 mole per dm cube. Then my V1, I don't know. My C2 is the one they asked me, they gave me in the question, which is 2 molar dm cube. And then my V1, they say is, will you prepare this molar concentration of H2SO4? That's 1 dm cube. 1 dm cube. Take it as 1 dm cube so that my V1 becomes C2 V2 over C1. And at that point, we are going to be having C2 is 2 times V2 is 1 over, then C1 is 17.3. And this will give us, if you do your calculation very well, this will give you 0.11561 dm cube. This is the volume you need to measure out. You need to measure out this volume. So you remember what we do now. What you are going to do now is you are now going to, if it's like it was in the exam, not if it is in the exam. If you're asking, as we are asked this in the exam, first of all, give them concentration in gram per dm cube. Then you now give them concentration in mole per dm cube. Then you now give them volume of the solution needed, which you calculated as this. So concentration in gram per dm cube, concentration in mole per dm cube, volume of the solution needed to prepare 2 molar concentration of HCl. This is it. Then you will now have statement. The statement now is that hence we are going to measure out 0.11561 dm cube volume of the acid using measuring cylinder or burette. You are going to measure out using your burette or measuring cylinder. You measure out this volume, turn it into a volumetric flask. Use a burette to measure out this volume, turn it into a volumetric flask, and using water, make it up to 1 dm cube. Then the solution is prepared. You have finished preparing the solution. Use your burette, measure out this volume. That volume you have measured out, pour it into a volumetric flask. When you are putting it into a volumetric flask, something like this, let's say this is a volumetric flask, measure this total 1 dm cube, then you have 0.115. That is, you use your burette to measure out that 0.115, then you pour it into a measuring cylinder. Let us say, see where in there. You now use water, top and up. Since they say now 1 dm cube, top and up to 1 dm cube. Then this solution, its concentration is 2 mole per dm cube. So that is the answer to that question in that year. That's the answer to that question in that year. Okay, what of somebody can use, another way is that someone can use a formula to obtain this, So if I don't want to go through this, but I think this method I use is the best first. But if you want to use formula method, you can use it. Let's see. So first of all is to obtain concentration in mole per DMQ. So we are given that C is equals to 2 molar concentration. The molar mass is 98 gram per mole, and we have that Sg is 1.84, and we have that P percentage is 92%. So what you're going to do is concentration in mole per DMQ, let's call it C0, is equals to 10 times P times Sg over molar mass. You can use this formula. 10 times P times 10 is constant. P is percentage. Okay, 92. P percentage. Look at it. Sg is this. The molar mass is that. So we are going to be having 10 times 92 times 1.84 over 98. And when you do this calculation very well, you'll also be obtaining 17.3 molar concentration. So this is the concentration of the acid you are given. The next thing is to calculate the volume. How do you do? So volume FVO is equals to molar mass times CD times VD over 10 times P percentage times specific gravity. Check this volume out. So we have molar mass is 98. CD is the concentration given to you, 2. VD is the one you want to obtain, 1 dm cube. That's the volume of the second one, 1 dm cube. This is 1 dm cube over 10 is constant. P is 92%. So it's just 92 you are going to write here. Then Sg here is 1.84. When you do this calculation very well, you will be obtaining 0.11. I think that, let me press it and be very sure. I have 98 times 2 times 1 over 10 times 92 times 1.84. And that will give me 0.11578 dm cube. You get that now? So this is the concentration of the acid in mole per dm cube. This is the volume needed. Then the next thing you just need to put down is your statement. You will now say that you pipette out this volume and put into a volumetric flask, which is calibrated up to 1 dm cube. Then you use water to top it up to the mark, and that's all. So that question, I've answered it in 2 ways, using dilution formula and using normal formula. So you have to mark this. If you are using this formula, you have to mark this, and you have to mark this. This for the volume, this for the concentration. Or if you are using the other one I just used, so you know what to do. So we move on. What do we understand by this? We say this is a quantitative chemical analysis which determines the volume of a solution with accurate known concentration. Volume of a solution with accurate known concentration required to react quantitatively with the analytes. Required to react quantitatively with the analyte. The analyte in this case is a concentration to be determined. A solution concentration which is to be determined is the analyte. Okay? We also should note that the volume of titrant required, to just completely react with the analyte, the volume of titrant required to completely react with the analyte is called titer volume. It's called titer volume. The volume of titrant which is required to completely react with the analyte is called the titer volume. You must have heard all these things in practical chemistry. Okay. Having known this, we go to some other things again. The next thing we are going to look into is what we call the dilution formula. Dilution formula. I'm just reminding us some things. Dilution formula. You know that dilution formula is C1V1 equals to C2V2, where C is a concentration of the first solution and its volume, concentration of the second solution and its what? Volume. That's what we have as C1V1, C2V2. That is dilution formula. Okay, we're going to take an example to see how this dilution formula is being. Now, looking at the board, we see an example. We say, what volume of distilled water should be added to 40 centimeter cube of 2 molar concentration? This M means mole per dm cube. To 2 mole per dm cube of H2SO4 to obtain 0.2 mole per dm cube of the solution. Now, one thing you must know when you are using the dilution formula, we have C1. How do I know I'm going to use dilution formula here? Now, the question says, what volume? That means I'm looking for volume. I'm looking for volume of a distilled water should be added. When you're adding water to something, then you are diluting. So we have volume. We have should be added to 400 centimeter cube. What volume of distilled water should be added to 400 centimeter cube of this? This volume is for this concentration. So the main thing here is that you need to know which, you are going to be using C1 V1 equals to C2 V2. But the thing there is that which one is going to be C1, which one is going to be V1. Now see the question. What volume of a distilled water? Now, what volume of a distilled water? We are yet to get that volume. Should be added to 400 centimeter cube of this. That means this one is present already. They are not asking you what volume should we add. That means since 400 centimeter cube of this H2SO4 is present, then we want to obtain this concentration. We are trying to obtain this concentration. That means this concentration will come after the dilution. So that means this concentration becomes C2. Then the volume to be gotten, since this volume belongs to this concentration, that means the volume we are looking for this concentration. Hence, that volume we are looking for should be V2. Hence, so that means here my C1 is going to be 2 molar concentration. My V1 is going to be 400 centimeter cube. Then my C2 will be 0.2 molar concentration. Then my V2 is actually what I'm looking for. Please, you read the question very well to know if you are looking for V1 or V2 or C1 or C2, and based on the arrangement. Now, from this thing, I'll say that V2 is equals to C1 V1 over C2. And my C1 is 2. My V1 is 400. My C2 is 0.2. And if we do that work perfectly, we are going to be having 4,000 centimeter cube. We are going to be having V2 to be 4,000 centimeter cube. Now, we have our V2 to be 4,000 centimeter cube. Now, we now conclude. Since we are going to add this, what we need to add is 4,000 centimeter cube. You will now say that, hence, the volume of distilled water needed, hence, the volume of distilled water needed becomes V2 minus V1, which is 4,000 centimeter cube minus 400 centimeter cube. And that will produce 3,600 centimeter cube. This is the volume you need to add. So if you add, the total volume we are looking for is going to be 4,000 centimeter cube. So since we have 400 centimeter cube already, we will minus this 400 from the answer we've gotten. So that if you add 3,600 centimeter cube to 400 centimeter cube, you will now have second volume. That is the total volume to be what? 4,000 centimeter cube. This happens when you find V2 before V1. If they give you V1 and you are looking for V2, when you get your V2, please try to minus it from the V1 so that you have the total, so that the total volume of the V2, because V2 is V1, V2 is the total final volume. That means you have done everything. So this final volume is supposed to be 4,000. Since it's going to be 4,000, we already have 400. So we just need 3,600 to add to this 400 to make it a total of 4,000. I believe this is very clear. I will take one more example that we are not going to obtain V2. Instead, we are going to be looking for what? V1. Now, if we look at this second example on the board, it says calculate the volume of 12 molar concentration HCl that should be diluted with distilled water to obtain 1 dm cube of 0.050 molar concentration of HCl. Remember that after the word obtain, the next things you are going to be seeing are the second one. So to obtain, then that's something we want to obtain. So that means this one is V1, this one is V2, this one is C2. They come after obtain. Now, if you don't mind, you go back to the first question. It says, what volume of distilled water should be added to 400 centimeter cube of 2.0 dm cube H2SO4 to obtain, they now say 0.2. And we say that 0.2 becomes our V2. Isn't it? That's 0.2. Sorry, our C2. That 0.2 molar concentration becomes our C2 because it came after the word obtain. So these ones has come after the word obtain. So they are going to be 2. Why this becomes my C1? So that means the volume of this one is going to be my V1. So I'm going to be having V1, I don't know. Then C1 is 12 molar concentration. V2 is 1 dm cube, and or you can call it 1,000 cm cube, and then C2 is 0.050 molar concentration. Okay, at this point we are looking for V1. From C1 V1 equals to C2 V2, we have that V1 should be equals to C2 V2 over C1, and that will become 0.050 times 1 dm cube over 12. And if you do that very well, you are going to be having 4.2 times 10 raised to the minus 3 dm cube. That's the volume you are going to get. Now, in this case now, because we are getting V1, we will not go and say V2 minus V1. It is when you get you are given V2, then you now got V1. You are giving V, just like the first this one. Now we got V1. We're not going to say V2 minus V1. That if you are given V1 and you look for V2, you will now conclude by saying V2 that you have got in minus the V1 given. Otherwise, if you get V1, you are not going to do that last calculation. Okay, so that is what we are trying to talk about here. So that 2 example is for dilution formula. We're going to take one more example under this dilution formula. Very, very important example. If we look at the example 3 on the board, it says the label on a stock bottle of HCl reads specific gravity equals to this. Percentage by mass is 36% of HCl. Then also should calculate the concentration of this in gram per dm cube, that is mass concentration, and also its concentration in mole per dm cube, that is molar concentration. Also, we should calculate what volume of this acid is required to make 1 dm cube of 2 molar concentration of HCl. Now, let me explain something. This aspect of dilution formula we are learning, its main application in the lab is to prepare standard solution. Like when you want to perform experiments in the lab, titration experiment, the solution that is going to be used need to be prepared. They don't come like that from the market. You prepare them. It comes like you have a bottle. If you get a bottle of ACL, very expensive, then you have on the label, you have all this on the label. Now, maybe you know the concentration you want to be prepared so that the children will use it for experiment. You know the concentration of the this, because if you give it out directly the way it is inside the bottle, it's very, very corrosive. It's very, very corrosive. So you have to prepare a certain concentration for the students to use to prepare do their titration. And this solution, this concentration of what you're going to prepare is not going to be that corrosive, because you know there can be lab accident. You can pour on some persons, and if they are not careful, there will be corrosion of their skin. So also, if you eventually have an opportunity to visit your secondary school and you go to see your chemistry master, and maybe that day they are about to do chemistry practical, and he's trying to prepare an acid solution for the practical, and maybe according to WAEC say they should prepare 1 dm cube of 2 molar concentration of ACL that they are going to use for the experiment. So when they are prepared the 1 dm cube of this concentration, 1 dm cube having this concentration, then they will now start sharing it in all the beakers that are in the lab, okay, for students that will come and use them. So peradventure the chemistry master has emergency and asks you now that you have already gone to the university, please, I beg of you, can you help me prepare 1 dm cube of 2 molar concentration of ACL? You know, what you're going to be doing is dilution, and that is what we want to learn now. So all you need to look at is the specification on the bottle. These are the specification on the bottle. We are assuming it might be more than this. So, but observe the specification on the bottle. Then what you're going to do is to, first of all, find the concentration of this in mole per dm cube. But before you can get it in mole per dm cube, you have to get it in mass concentration, in gram per dm cube. From mass concentration, you can get it in mole per dm cube. That becomes the concentration you want. Then you will now get the volume, needed volume in 1 dm cube. Then you will now dilute it to that mark. Then you can now share it. So let's learn what to do. So at this point, we are solving. Okay. I will first of all let you know that SG, which is called specific gravity, is equals to 1.18. What does it mean? This means that 1 centimeter cube of the solution, 1 centimeter cube, for when they say SG is equals to 1.18, what does it mean? It means that 1 centimeter cube of the solution, 1 centimeter cube of the solution weighs 1.18 gram, or 1000 cm cube, which is equals to 1 dm cube of the solution weighs, okay, here will now be this times 1000, 1180 gram. So mark that. First of all, what we need to learn here is that when they say that the specific gravity is 1.18, it means that if you measure out 1 centimeter cube of that, because this is a solution inside the bottle, if you pour out 1 centimeter cube, you measure out 1 centimeter cube of that solution, it will be, if you weigh it, it will weigh 1.18 gram. That is what they are telling you. If you weigh 1 centimeter cube of that solution, it will weigh 1.18 gram, and that is how they got their specific gravity. Or if you weigh 1000 cm cube of that solution, it will weigh 1.18 gram times 1000, which will give you 1180 gram. I've explained what specific gravity means. Okay. The next one I'm going to explain is what 36% by mass mean. Okay, let's write 36% by mass. This one means that 100 gram of the solution, that 100 gram of the solution contains 36 gram of the solute. It means that 100 gram of the solution contains 36 gram of the solute. Now, they say 36% by mass of HCl. Remember, this solution was prepared by getting the salt of HCl, then dissolving it in water. So we are trying to tell you that if you weigh 100 grams of this solution, 100 grams of this solution, it contains 36 grams of the HCl that was dissolved in that solution. 100 grams is to, that is 36% of the solution is HCl. 36%. So that means that is inside 100 grams of the solution, you will see 36% of HCl. Inside 100 grams of the solution, you have 36% of HCl. So 100 grams of the solution contains 36 grams. 100% of the solution contains 36% of the solute, which is solute now, which is HCl. You know what we call solute and solution. Solutes are dissolved in solution. Solutes are dissolved in solvent to form solution. Hope you understand. Solutes are dissolved in solvents to form solution. So we are trying to say that this solution now, solute plus solvent is equals to solution. Now, this solute now is HCl. Now, the solvent should be water here. Then you have the solution now. So what you're having is the solution. And they are saying that in this solution now, which is 100% now, that if you 100% of this solution now contains 36% of this guy, that means if 100% of this solution contains 36% of this, that means the percentage of water there is going to be 100 minus 36. 100 minus 30 is already 70. Take away 6 from it, you are going to be having 100 minus 36. We're going to have 64. 64% now. That means we have 36% of this plus 64% of this gave us 100% of the solution. So we're saying that inside 100% of the solution, we have 36% of HCl, which is the solute. Or inside 100 grams of the solution, we have 36 grams of the solute, which is the HCl. So when you see this in the label, that 36% by mass of HCl, know that you have only 36% should. If it doesn't go with what you want, you know the exact one to buy. We have explained the label on this now. So let us go ahead to see how can we get concentration in gram per dm cube, concentration of this thing in gram per dm cube, and also its concentration in mole per dm cube. That is the next thing we want to look into now. Okay, so we want to calculate for concentration, for mass concentration, which is concentration in gram per dm cube. Okay, okay, so we say since 1 dm cube of the solution weighs 1180 gram. 1 dm cube of the solution weighs 1180 gram. Okay, therefore 1180 gram of the solution will contain, if 1 dm cube of the solution weighs this, then this mass of the solution will contain 36 over 100 times 118 gram over 1. That will give me 424.8 gram of HCl. Now, what's something? Remember that the label says that for them to say specific gravity is 1.18, it means 1 centimeter cube contains 1.18 gram, or 1 dm cube contains 1180 gram. So we now say, since 1 dm cube of the solution will weigh this, if you measure out 1 dm cube of the solution, that is 1000 cm cube of the solution, and weigh it, it will weigh this. Now, therefore, 1180 gram of the solution will contain, what does it contain? If you weigh out 1180, that is 1 dm cube, you pour out 1 dm cube of the solution and you weigh it, it will give you this weight. So it means that this weight contains Since it is 36% of HCl, it will contain this times this, this times this, 36% times this for the dm cube, which will give 36% times 118 gram over 1, which will give us this. So it contains this amount of what? HCl. It contains this amount of what? HCl. Now, this means that 1 dm cube of the solution contains 424.8 grams of HCl. Hence, mass concentration, listen now, listen, 1 dm cube. This means that 1 dm cube of this solution will contain 424.8 grams of this HCl. That means inside 1 dm cube, that is volume, inside 1 dm cube volume, you have this amount of HCl. Hence, concentration in mass, which is this, per dm cube, that is how many mass, this thing means how many mass measured in gram, that is mass, how many mass of this is contained in 1 dm cube, mass per dm cube. So we have seen that it is this percent times this in dm cube will now give me 424.8 gram per dm cube. So it will have 424.8 grams of HCl inside 1 dm cube. How did you get that? 36 divided by 100 times 1.18 times 1000, which will give you 1 dm cube. Once you do that, you will get the concentration in gram per dm cube. I believe this is well understood. So that is how to get concentration in gram per dm, which is also called mass concentration, because mass is G. So how do you get mass concentration? The percentage by mass, which is 36%, that is 36 divided by 100. So if you are doing it in an exam, because there is no time, you just say, oh, I have 36 divided by 100 times, you multiply this one by 1000, which will give you 118 over 1. And that will give you 424.8 gram. Do you get that? Because this is 36 over 100 times 118 over 1 will give you this. Then this in, because this is dm cube, so it's now going to be 424.8 gram per what? dm cube. That is a mass concentration. Very fast. You get the mass concentration. So the next thing we are going to be getting now is the concentration in mole per dm cube. That is the molar concentration. We want to get the molar concentration now. Now, we must know that molar concentration is equals to mass concentration over molar mass. You have to know this. That molar concentration, that means concentration in mole per dm cube is equals to concentration in gram per dm cube over molar mass. What we are talking about here is HCl. And what is the molar mass of HCl? It is 36.5. Remember that the molar mass of HCl is equals to 36.5 gram per mole. Molar mass of HCl is 36.5. So we are looking for molar concentration. So it's going to be molar concentration, mole per dm cube, is equals to mass concentration. We have gotten it as 424.8 over then 36.5, and that will give me 11.6 mole per dm cube. Okay, so I've gotten my concentration in mole per dm cube, and I've also gotten it in gram per dm cube. This is gram per dm cube, while this is mole per dm cube. So I think I've explained with all this time how to get your concentration of this solution in gram per dm cube and its concentration in mole per dm cube. Okay, then having known this, we are going to now go to how to calculate the volume. They say, what volume of this acid now do you need to make up 1 dm cube of 2 molar concentration? Now we need 2 molar concentration of this. So that is the next thing. I'm going to go to volume now. We're going to go to how to get the volume. Now, to get the volume, we are going to be using C1V1 equals to C2V2. Do you remember that? So in this case now, the C1, the molar, in this one we use molar concentration. Remember that we got this molar concentration, which is our C1, to obtain or to require to make or to obtain this. To obtain this, this becomes my C2V2, because they came after the word to obtain, because they say what volume of this acid is required to obtain this. So that means this is my C1 and I'm looking for its C2. So my C1 is we got to be 11.6 mole per dm cube. Then I'm looking for V1. I don't know. Let me call it X. But my C2 I will be needing is 2 mole per dm cube. And my V2, they say I should use 1 dm cube. Do you get that? So I'm looking for V1. V1 becomes C2V2 over C1. And this becomes 2 times 1 over 11.6. And that will give me 0.172 dm cube. 0.172 dm cube. Do you get that? So this is the volume of the acid that is required to make up 1 dm cube of this. So what does this really mean? Let me explain. Now, you have gotten the concentration of this acid that you have bought in mole per dm cube to be this. This is the concentration of the acid you bought in mole per dm cube. Now, you want to know the volume of this acid you are going to collect, then put inside a volumetric tube and make it up to 1,000 cubes so that its concentration will be this. So what you are going to do now is that since you have gotten the volume to be this and you calculated this volume using this second concentration, which is 2 mole per dm cube. So you will now just take this bottle, take a volumetric flask for measuring volume, measure out 0.127172 dm cube from that bottle that you bought from the market. Measure out 0.172. You measure out 0.172 dm cube. If you are not doing it in dm cube, you can do it in cm cube. You can convert dm cube to cm cube, but there are volumetric flasks that are measured in dm cube. So you measure out 0.127 dm cube. When you measure that out, you are now going to pour it into. Okay. The next subtopic we are going into now is acid-base titration. So in this acid-base titration, we'll be seeing, first of all, let us know what is indicators. When you want to do the titration proper, you need to have your indicator. Let's know what an indicator is. You can write. Indicators are weak organic acids. Indicators are weak organic acid or base that changes color depending on pH of the solution. They are weak organic acid or base that changes color based on the pH of the solution. Full stop. They are used in acid-base titration to dictate the end point of the reaction. They are used in acid-base titration to dictate the end point of the reaction and also to test acidity or alkalinity. They are used in acid-base titration to detect the end point of a reaction and also to test for acidity or alkalinity. Okay, that is for indicators. Let us look at buffer solutions. What are buffer solutions? Let's write. Buffer solutions are solutions which resist change in pH on further addition of any acid or alkali. I repeat, buffer solutions are those solutions that will resist change in the pH on further addition of an acid or alkali. Okay, full stop. It consists of either a solution of a weak acid in the presence of one of its salt. It consists of the solution of a weak acid in the presence of its salt. Example, ethanoate, ethanoic acid, that is a weak solution, a weak acid in the presence of its salt. Example, ethanoic acid, sodium ethanoate, sodium ethanoate. So if you are asked to give some examples of buffer solution, ethanoic acid is a buffer solution which is a weak acid in its salt. Sodium ethanoate is also a weak acid in its salt, in the presence of its salt. Or solution of a weak base in the presence of one of its salts. Example, ammonia solution. Ammonia solution. We have ammonium chloride. Now, I've just given two examples of a buffer solution. I'll repeat it again for better understanding. It says, buffer solution consists of either a solution of a weak acid in the presence of its salts. Example, ethanoic acid, sodium ethanoate. Or a solution of a weak base in the presence of one of its salts. Example, ammonia solution or ammonium chloride. Okay. So that is two examples of a solution. Now, buffers are mainly used in the laboratory in preparing solution of known concentration or of constant pH. I repeat, buffer solutions are mainly used in the laboratory in the preparation of solutions of known concentration or a solution that has a constant pH. Now, from this, I have defined what a buffer solution is. I have told us the content of a buffer solution. I have given us the example of a buffer solution. And finally, I have given us the use of buffer solution. I believe you have that. The next one I'm going to look into now is pH. What is pH? This is not Port Harcourt, sha. pH. This is the measure of hydrogen ion concentration in the solution. This is the measure of hydrogen ion concentration in the solution. pH ranges from 0 to 14. pH ranges from 0 to what? 14. So pH less than 7 is acidic. Then pH greater than 7 is alkaline. While pH equals to 7 is neutral. I believe this, we already know this from secondary school. So pH less than 7, pH greater than 7, and pH equals to 7. Okay. Then the next thing we are going to look into is choice of indicator in acid-base titration. Choice of indicators in acid-base titration. Remember that we have defined indicators. I've defined what an indicator is. Then how do you select indicators when you are doing your acid-base titration? Let's write. The choice of indicator depends on the strength of the acid and base. The choice of indicator depends on the strength of the acid and base, which is governed by the pH at the end point and the pK of the indicator. That is what we call the pK of the indicator, and that is what we call the pH of the end solution. I repeat, the choice of indicator depends on the strength of the acid and its base, choice of the acid and its base depends on the choice of acid and base you are using, and it is governed by the pH at the end point and the pK of the indicator. The pH at the end point pH, and also pK of what? Indicator. So these are the two things that governs the type of indicator you are going to use. Depends on the type of acid, the strength of the acid and base you are using, one. It depends on the end point, the strength of the acid and the base you are using depends. The solution you get at the end point depends on the strength of the acid and base you have used. Then the pH of the end point also it depends on it. Then the pK of the indicator. Let's see a table that will show us a definite view of what we are trying. I believe we can see what's on the board. So like I said, we are talking about indicators, choice of indicators in acid-base titration. Let's start from this table. You need to zoom to see what is on the board, please. We have indicators. We have in acid, in base, in alkali. We have the pK of the indicator and we have the pH. Now, when the indicator is a litmus paper in acid is red. In base, it is purple. While in alkali, it is blue. The pK of litmus paper is 7. So the pH will run between 6 and 8 to contain that 7. So the pH is between 6 and 8. So if you have a solution whose pH is between 6 and 8, you can use a litmus paper. That's what it means. Methyl orange is an indicator. When can you use it? If you put methyl orange in acidic solution, it's going to turn pink. If you put it in base solution, it's going to turn orange. Then in alkaline solution, it's going to turn yellow. The pK of methyl orange is 3.7. So its pH will run from 3 to 4. When you have a pH between 3 and 4, you can use a methyl orange as the indicator. Phenolphthalein, in acid, it has no color. In base, it has no color. But in alkaline, it has pink. Hence, its pK is 9.1. So it can be used when the pH is between 8 and 10. Between 8 and 10 is basic, or you can say alkaline. This one is acidic. This one is basic. Methyl orange. In acid, methyl orange is pink in an acid solution. In a base solution, methyl orange is red in a base solution. In alkali, methyl orange is yellow in alkali. While the pK of methyl orange is 5.1 and the pH is between 4 to 6. Okay. Having known that, you need to write down this and memorize it. Then come here. Let's see it in acid and base. This A/B means acid stroke base in acid and base solution. Now, pH of the end point, because when you do when you mix an acid and base, depends on the, remember I was saying, it depends on the strength of the acid and the base that is being used. That's how then it will tell about the pH, then the pH will tell about the indicator. Okay. When you are using strong acid versus strong base, strong acid, strong base, the final solution will be neutral. That is 7. And if it is 7, which is neutral, you can use any indicator such as methyl orange or phenolphthalein, methyl orange and phenolphthalein or phenolphthalein, any indicator, but choose between methyl orange and phenolphthalein. If you use methyl orange, then you are going to be having, since the solution is neutral, that is the solution is neutral. Okay, let's continue. I'll show you something. Methyl orange or phenolphthalein. Strong acid, weak base. The pH is between 5 to 6. Strong acid, weak base. The pH is between 5 to 6. If you use methyl orange here, you have methyl orange. Since this is basic, the end point, it will be orange. If you use phenolphthalein, you have colorless. I believe you know that in the lab. That's what I wanted to say before. So if you are using strong acids versus weak base, the final pH will be between 5 to 6. 5 to 6, not 5.6. 5 to 6. 5 to 6 is still fair acidic. So the indicator to use when you are using a solution of strong acid and weak base, you use methyl orange. So methyl orange here will produce pink. Methyl orange here will produce pink, just like that. If you are using weak acid and strong base, the pH of the end point will be between 8 to 9. Between 8 to 9. You see it? If the pH is between 8 to 9, you are going to use phenolphthalein. When pH is between 8 to 9, you're going to use phenolphthalein. When pH is between 5 to 6, 5 to 6, look at it, 5 to 6, you are going to be using methyl orange. Do you see that? When pH is between 8 to 9, 8 to 9 is around here, you use phenolphthalein. Okay, when you are using this kind of weak acid, weak base, the pH is variable. Hence, there will not be suitable indicator. There will not be suitable indicator. Watch this one. When the pH is between 6 to 8, 7 falls here. If it is 7, you are going to be using any indicator, either methyl orange or phenolphthalein. So you can use methyl orange or phenolphthalein for this one once it falls to 7. Here we also use a litmus paper. So I believe this and this should be recorded down. That is for choice of indicator. For choice of indicator when you are doing your titration. The next subtopic we want to see now is recording in titration experiment. How do you take your record? Number 1, you state the size of the pipette used in DMQ. State size of pipette used in titration. That's number 1. Number 2, name the indicator used. Indicator used. Number 3, record the titration in tabular form. Record the titration in tabular form. Okay. Then number 4, obtain average value of acid used, which we call the titer value. Okay. These are the things you need to know. First of all, you state the size of the pipette. You can be given a table and they ask you to criticize the table. I mean, tell us where the problems about this table. Now, first of all, check if the size of the pipette used is indicated in DMQ. Okay, even though it's in CM cube, you know what to do there. First of all, check the size of the pipette used. It must be given to you in DM cube. If it is not there, tell them it is not there. That's one error. Name the indicator used. Look, if they indicated the type of indicator being used, if they did not indicate it, it's an error there. Okay, you also now look at if the reading has been tabulated in tabular form. If it's not in tabular form, it's an error. It must be in tabular form. Then you now look if they've given the value of titer value of acid or the volume of acid being used. These are the things you need to get about it. So we're going to draw out. I'm going to draw out a reading there. But what you must know is that for you to get titer value, note that the titer values are those values that did not differ from each other with more than 0.2 centimeter cube. They must not differ from each other by more than 0.2 centimeter cube. What do we mean? I'm going to show us in the example that I'm going to draw next. Now, if we look at this table, you will see that the burette reading was given in cm cube. The rough titer, the first titer, the second, one is rough, one is first and second. Now, initial, final, this should be a reading gotten in the lab, okay? Now, this plus this minus this gave us this. This minus this gave us this. This minus this. That means final volume minus initial volume gave us this. Final volume minus initial volume gave us this. Final volume minus initial volume gave us this. Now, for me to get the volume of acid used, that is the titer value. For me to get the titer value now, I'm going to use it's not once I will do this plus this divided by 3. No. The values I'm going to use are the ones that do not differ from each other by more than 0.02. By more than 0.02. They must not differ from each other by more than 0.02. I think I've said that before. They must not differ from each other by more than 0.02 centimeter cube. Okay, how do I know that? You do this minus this. If you take your calculator, do 24.4 minus 24.35. 24.4 minus 24.35. You will say that that will give me 0.05. These two did not differ, it never even reached 0.02. This is 0.05. He said it must not be more than 0. Okay, now it must not be more than 0.2, sorry, 0.2 centimeter cube. So if I do this minus this and it is more than 0.2 centimeter cube, I will not use it. But if you do this minus this, it will give you 0.05. You can use it because it's not even up to this. So what of this minus this? 24.4 minus 24.3. It gives me 0.1. It is still not up to this, so I can use this. This minus this, 24.35 minus 24.30. It gives me 0.05. So all of them I can use. So my theta value can be this plus this divided by 3. I will get the theta value. But if I find out that any of them differ from the other by more than this, I will not use that. Please note that. That is all. That is much we need to know about recording titration. So they can ask you to criticize this. You check for the measurement. Are they there? Okay. Like in this case, now I'm supposed to have centimeter cube here. I'm supposed to have centimeter cube here because they are all volumes. Okay. You need to know. They are going to tell you the size of the pipette used. They are going to tell you the name of indicator used. They are going to give you theta volume. Check if the theta volume were gotten correctly. Check if you minus all these things, will they give you the exact answer you are looking for? All these things are how we criticize a table in titration experiment. Okay, we'll go to another sub. Welcome back again. We are going into preparation of standard solution. Now, standard solution is this solution we are using in the lab. Do you get that? Okay. First of all, let's define what a standard solution is. That's right. A standard solution is a solution of known concentration. A solution whose concentration is known is called a standard solution. Okay, full stop. Let's write. A standard solution can be prepared from a primary standard solution. A standard solution can be prepared from a primary standard solution. Now, the two major standard solutions are primary standard solution and secondary standard solution. Remember, we said that standard solutions are solutions of known concentration. The solution whose concentration is known is called a standard solution. And this standard solution can be prepared from a primary standard solution. So we have two types of standard solution. We have secondary standard solution. We have primary standard solution. Now, there is one question that may ask us in the exam. They say, why is it that standard solution of a common acid and base cannot be prepared by direct weighing? Why is it that the standard solution of an acid and base or alkali cannot be prepared by direct weighing? The reasons are, number one, some of them are volatile and corrosive. Example, HCl, HNO3, and ammonia. HCl, HNO3, ammonia. The reason these ones cannot be prepared by direct weighing is because, one, some of them are volatile, some of them are corrosive. While H2SO4 is hygroscopic, some of them are hygroscopic. Example, H2SO4. Some of them are volatile, one. Some of them are corrosive. Example of those that are corrosive, we have HCl, HNO3, NH3. Then some of them are hygroscopic. Example, H2SO4, hygroscopic. Some of them are solid, that are deliquescent, and hence absorbs moisture from the environment. Some of them are solids, and these solids are deliquescent. Hence, if you bring them out to prepare them, they will absorb moisture from the what? Environment. And they can also absorb CO2 from the atmosphere. They absorb water from the environment because they are hygroscopic, and they can also absorb CO2 from the atmosphere. Example of this one are KOH and NaOH. These ones are hygroscopic. These ones will absorb CO2 from the atmosphere. This one will absorb water, is hygroscopic. These ones are corrosive. All these are solutions. They cannot be prepared. We say, why is it that standard solution of acid and alkali or base cannot be prepared by direct weighing? The reason is that one, some of them are volatile and corrosive. Volatile and corrosive. These ones, they are volatile and corrosive. Some of them are hygroscopic. This one is hygroscopic. Some of them are solid that are deliquescent. This one is hygroscopic. Some of them are solids that are deliquescent and hence will absorb moisture and CO2 from the atmosphere. We are referring to this. Okay, so that answers that question. So in the exam, if you are being asked, why is it that there is some standard solution of acid and base cannot be obtained by direct weighing, you can tell them that some of these solutions are volatile and corrosive. Example, some of them are hygroscopic. Example, some of them are solid and hence they are deliquescent, so they can absorb water, moisture from the atmosphere and CO2. Example. And these are the reasons why you cannot prepare them by direct weighing. Okay. Now, since we have two types of standard solution, we have the primary standard solution, we have the secondary standard solution, and the standard solution is prepared from a primary standard solution. Let's see if you are asked to define what are primary standard solution. Let's write. These are solutions which can be obtained in high state of purity. Primary standard solution are solutions which can be obtained in high state of purity, anhydrous, non-deliquescent, non-hygroscopic, readily stable, readily soluble in water or in liquid of the required solvent, and suitable for preparing standard solution. I repeat, a solution, a primary standard solution is a solution which can be obtained. One, properties of a primary standard solution is what I'm trying to write down. They are solutions which can be obtained, one, in high state of purity. High state of purity. They can be obtained in high state of purity. All these things must be contained in your definition. Two, they will be anhydrous. Three, non-deliquescent. Four, non-hygroscopic. 5, very soluble in water or liquid of required solvent. 6, suitable for preparing standard solution. These are properties of a primary standard solution. They have high state of purity, they are anhydrous, non-deliquescent, non-hygroscopic, very soluble in water or liquid of required solvent, suitable for preparation of standard solution. Now, you might be asked, what are examples of these primary standard solution. Let's see, e.g., anhydrous sodium carbonate 4. We have Na2CO3. Anhydrous sodium carbonate 4 is one example, and another example is benzoic acid, which is C6H5CO2H, benzoic acid. So these are two examples of primary standard solution. Primary standard solution. Okay, having known this, we want to now also define what are secondary standard solutions. We have seen primary standard solutions. We also want to see what are secondary standard solutions. Let's write. These are solutions in which the concentration of the dissolved solute has not been determined from the weight of the compound dissolved. I repeat, these are solutions in which the concentration of the dissolved solute has not been determined from the weight of the compound dissolved, but by reaction, that is titration, of the volume of the solution against a measured volume of primary standard solution. Okay? Remember I said that standard solution is prepared from a primary standard solution. Though we have two types of standard solution. We have primary standard solution and we have secondary standard solution. We have seen the definition of primary standard solution. For the definition of secondary standard solution is what we are saying, that it is a solution in which the concentration of the dissolved solute, you know what is solute? Remember that I said we have solute, solvent equals to solution. Now, a solution in which the concentration of the solute has not been determined. You have not known the concentration of the solute. A solution in which the concentration of the solute has not been determined from the weight of the compound dissolved. A solution in which the concentration of the solute have not been determined from the weight of the compound dissolved, but by titration. Then that means a solution in which the concentration of the solute was not determined by weighing, rather by titration of the volume of the solution against a measured volume of primary standard solution is called a secondary standard solution. The solution, the concentration of the solute was determined not by weighing, but by titration of the volume of the solution, of the volume of this solution against a measured volume of a primary. When you get the volume of this solution and you titrate it against a measured volume of a primary standard solution, what solution you have gotten is what we call standard solution. I believe this is very clear. Let me repeat again. A solution in which the solute of that solution, the concentration of the solute of the solution was not gotten by weighing, rather by titrating against a certain volume of a primary standard solution. That type of solution is called secondary standard solution. Example of secondary standard solution, we have sodium hydroxide. Mark this. That is one example of standard secondary standard solution. Okay. Now, when we did about dilution rule formulas, we did our C1 V1, C2 V2. We saw how to prepare solution standard solutions. Okay. So I think that is off now. So we go to another subtopic. We'll go to another subtopic. These are things that we might likely see in the exam. Go to another subtopic. In this case, we want to say, I know we must have heard about Na2CO3. This is always used in acid-base titration, yet it is not a base. So we want to see, why is this used in acid-base titration, yet it is not a base. Let's write. Na2CO3 is a typical example of a salt of strong base and a weak acid. This is a salt of strong base, a salt of strong base. The base is NaOH, and a weak acid, which is H2CO3. This is a salt of strong base and a weak acid. Na2CO3 is a salt of strong base. The strong base there is NaOH and a weak acid. Okay. Now, when Na2CO3 is dissolved in water, when Na2CO3 is dissolved in water, it produces hydroxyl ion. When you dissolve this guy in water, it will produce hydroxyl ions. Hence, a water solution of Na2CO3 is alkaline. A water solution of Na2CO3 is alkaline. Hence, it is used in acid-base titration. Look at the balance equation here. We have Na2CO3 plus water. When you dissolve it in water, you have 2Na plus 2OH minus plus H2CO3. Now, if you observe, you see that we have an alkaline there. So, what do we really do? You know, in the lab, when you want to come and do your titration and, you know, to get a standard base or normal base for preparation might be expensive. But if the lab attendants have Na2CO3 in his cupboard, he can use it as base, though it is not a base, but he can use it as base. By doing what? He will just dissolve it in water. And once it dissolves in water, that solution contains is basic because of the presence of this guy. So you use it in the lab as a base. Okay, so that is why we use Na2CO3 in titration, because it's a sort of a weak, they asked in the exam, you said it is a salt of a strong base and a weak acid, which when dissolved in water produces hydroxyl ion. It is a salt of a strong base and a weak acid, which when dissolved in water produce hydroxyl ion. Hence, a water solution of Na2CO3 is what? Alkaline. Is alkaline. Hence, it is used in acid-base titration. So, note, a reaction in which water takes part in a chemical reaction is called hydrolysis. A reaction in which water takes part in a chemical reaction is called hydrolysis. Hence, dissolving this in water, this reaction is called, the process is called hydrolysis. A reaction in which water takes part in the chemical reaction is called hydrolysis. Hence, in water, sodium Na2CO3 undergoes what? Hydrolysis. It undergoes hydrolysis. We need to keep this in our memory. Okay, so I've told us what hydrolysis is. Should you see it in the exam? Okay, move to another subtopic. Now we look at what we have on the board. Calculation in normal acid-base titration. Okay, I have one example to drive the point home. It says A is a solution of HNO3 of unknown concentration. B is a standard solution of sodium hydroxide containing 4 grams per dm cube of a solution. 25 centimeter cube of this solution B requires an average, this is an, not and, required an average of 24 centimeter cube of the solution A for complete neutralization. Now, the question I'm coming says, state with reason suitable indicator for this experiment. 2, write balance equation. 3, calculate concentration of B, that is concentration of P, in mole per dm cube. Also, concentration of A in mole per dm cube. Then concentration in gram per dm cube of HNO3 in the solution A. Then use this to find your molar mass. So we are going to be solving all these one by one. We're going to be solving all these one by one. Okay. So we start from the first one that says state the reason with reason suitable indicator. If you observe, indicator here that will be used is either you use phenolphthalein or you use methyl. Why? Because it's a solution of strong acid and strong base. HNO3 is strong acid. NaOH is strong base. So a solution of strong acid and strong base surely we'll be needing any indicator of what? Methyl orange or phenolphthalein. So number one is answered. Strong acid and strong base. Okay. Number two, he said balance equation. So the balance equation will be HNO3 plus sodium hydroxide. Actually, will give us NaNO3 plus water. Salt and water. If you want to, we have plus minus, water. 1, 2, 3. NaNO3. You see that? So that's the balance equation. Plus goes to meet minus. Produce water. Hydrogen, two hydrogen. They have one oxygen making water. NOH3 is our minus here. Goes to meet plus here. Sodium, we add to N, so NaNO3. So that is the balance equation there. Now, we want to calculate the concentration of B in mole per dm cube. We want to calculate concentration of B in mole per dm cube. Now, if you watch, they say that the concentration of B in gram per dm cube there was given as 4 gram per dm cube. If you can go back to the question, it says A is a solution of HNO3 of unknown concentration. B is a standard solution of NaOH containing 4 gram per dm cube of the solution. So they gave us the concentration of B in gram per dm cube. So remember that concentration in mole per dm cube is equals to concentration in gram per dm cube over molar mass. Do you still remember? So if I know concentration in gram per dm cube, so what I need to get here is molar mass. So the molar mass here is 40 moles. Because we are talking about B, molar mass of B. Remember I said that B is a standard solution of sodium hydroxide. Sodium hydroxide. So Na 23 plus 16 plus 1. So we have 23, 16, 6. That is 9, 2, 3, 39. Okay. 23 plus 16, 39 plus 1, 40. So 40 moles. 40 moles. So therefore, concentration in mole per dm cube will now give me 4 gram per dm cube, 4 over 40. And if you do that very well, it will give us 0.100 mole per dm cube. So that is concentration of B in mole per dm cube. We have got concentration of B in mole per dm cube. You know that B is our base here. So they're supposed to give us the concentration of B in mole per dm cube in the question. But then they withdrawed it and gave us concentration in gram per dm cube. Remember that B is a standard solution, and a standard solution is a solution of known concentration. B is a standard solution of sodium hydroxide. So it's a solution whose concentration is known. Meaning that for its concentration to be known, they have the mole per dm cube on molar concentration. But they decide to give us the one of gram per dm cube and ask us to obtain the one of mole per dm cube. If you were to be in the lab, they will give you concentration of B in mole per dm cube already. And if you don't know concentration of B in mole per dm cube, you cannot get out of A in mole per dm cube. So if they give us concentration of B in gram per dm cube, from here we will find out the concentration of B in mole per dm cube. Now, we will now use that information to get concentration of A in mole per dm cube. And that is what we are going into next now. So we are going to concentration of A, which is the acid now, in mole per dm cube. If you observe we are going to be using CaVa over CbVb times equals to, amount of base, acid, over amount of base. This thing means concentration of acid times concentration of the times volume of the acid over concentration of base times volume of base equals to amount of acid over amount of base. Now, if you look at the information we have here, you will see that 1 mole of the acid requires just 1 mole of the base. 1 mole, the number here is 1. The number here is 1, the coefficient. That's what we're talking about. So therefore, 1 mole of acid A is equals to 1 mole of what? B. Therefore, Na is 1, Nb is also 1. Now, concentration of A, which is concentration of the acid in mole per dm cube, is what we don't know. So concentration of A becomes Cb Vb Na over Va Nb if you cross multiply this. Now, Cb is concentration of base in mole per dm cube, which we have gotten. Vb is the volume of base, which they gave to us. Na is 1. Va is the volume of acid they gave to us. So let's now calculate this from here. I'm going to be cleaning here for us to do it up here. So Ca equals to my concentration of my base. Now, to obtain the concentration of A, we have that the volume of acid Va is 24 cm cube. Convert it to dm cube. You're going to say 1000 cm cube gives us 1 dm cube, while 24 cm cube will give you x. Then you have divided the 24 by 1000, which will give you 0.024 dm cube. What of concentration of the base in mole per dm cube? We have calculated it to be 0.1. Then volume of the base, they gave it to us as 25 centimeter cube. And that is, you convert it to dm cube, you have this. Then we are now left with concentration of the acid, which is this formula that we have found out. So it is concentration of the base times volume of the base times amount of the acid over concentration of the volume of the acid times 1. And when you do that, you see that Ca becomes 0.1042 mole per dm cube. Okay, the last question says we should find concentration in gram per dm cube of HNO3 in the solution A. Now, we already have this concentration. HNO3 is the acid. We have concentration of the acid to be this in mole per dm cube. For us to get it in gram per dm cube is very easy, because we already know concentration in mole per dm cube is equals to concentration in gram per dm cube over molar mass. Then the molar mass of acid, which is HNO3, is going to be hydrogen is 1, nitrogen is 14, oxygen is 16 times 3, which will give us 60. We are looking for HNO3. Hydrogen is 1, nitrogen is 14. This will give us 40. That will give us 40. Okay. What am I saying? This plus will give us 63. Sorry, 63. So we will now have this becomes concentration in gram per dm cube equals to mole per dm cube times molar mass, where the molar mass is already 63. So we are going to be having 0.1042 times 63. And if you do that properly, you're going to be having 6.55 gram per dm cube. That is concentration of the acid in gram per dm cube. So this question has been well dealt with. A replication of it is in question in 2021 to 2022. Question number 1 is one application of it in the past question. We will see that when we get to past question. Okay, we'll see that when we get to past question. So we go to another aspect of subtopic. Okay, the next aspect of this revision class we are going into now is at the aspect of determining percentage purity in a substance. I will use this question on the board, which was gotten from question 1. This is question 1 II 2022/23. So that is where the question was gotten from. So I'm going to use this question to drive the point home. So we are going to calculate determine percentage impurity here. So I want us to follow me up as I solve these questions. Now, first of all, I would like us to know that percentage impurity, let me use the other side of the board. I would like us to know that percentage impurity is equals to mass concentration of impurity over mass concentration of impure. Mass concentration of impure times 100/1. Now, I repeat, percentage impurity is equals to mass concentration of impurity. Mass concentration of impurity over mass concentration of impure salt. Okay? Or you can say it's mass concentration of impurity in the salt over mass concentration, okay, mass concentration here, mass concentration of impure salt. Okay, now the main game now is how do we get mass concentration of impurity and how do we get mass concentration of impure salt? So, okay, so having known that for us to calculate percentage impurity, which we were asked, we are going to get concentration of the impurity in gram per dm cube and divide it by concentration of impure in gram per dm cube. So the steps we are going to use to get these two things are, we'll first of all say we have concentration of HCl in mole per dm cube, which was given. Concentration of HCl in mole per dm cube. That was given to us as 0.1 molar concentration. Okay, if that was given, then they gave us the volume of HCl. They gave us the volume of HCl to be 23.60 centimeter cube. Then you can convert this to dm cube by doing 23.6. You will get 2.36 times 10 raised to the power minus 3. That is if you say 23.6 divided by 1000. You have 2.36 times 10 raised to the power minus 3. Okay. The next thing you're supposed to have is now we have the concentration of the acid, the volume of the acid, the amount in mole of the acid, which is N equals to CV. So it's going to be C is 0.1 times 2.36. This is dm cube. 2.36 times 10 raised to the power minus 3 dm cube. And this will give us, if you multiply that times 0.1, it will give us 2.36. We are saying 2.36 exponential minus 3 times 0.1 will still give us 2.36 times 10 raised to the power minus 4. Okay, 2.36 times 10 raised to the power minus 4. Having gotten this information now, we will now write the balance equation. Writing out the balance equation now, we know that it is Na2CO3 plus 2HCl, which will give us 2 sodium chloride plus water plus CO2. Now, if you watch this equation, you see that 1 mole of Na2CO3 requires 2 moles of HCl. That's the next step. Then if 1 mole of this requires 2 moles of this, then how many moles of this will give us moles, 2.36 times 10 raised power minus 4. How many moles? So if you do that cross multiplication, you are going to be having 2.36 times 10 raised power minus 4 times 1 over 2. And that will officially give us okay, divided by 2. That will give us 1.18 times 10 raised power minus 4 moles. So you see, now I've got the moles of Na2. I've got the moles, the amount of acid, and I've got the amount of Na2CO3. Now, the next thing I'm going to do here is, I'm coming down here now. I have now established that now, do you know that if you go back to the question, they say 25 centimeter cube of the solution was pipetted. So the volume of this guy is 25 centimeter cube. So that is what I'm going to use next. I will now say, if 25 centimeter cube of NaCO3 requires this amount of base, 1.18 times 10 raised power minus 3, then 1000 centimeter cube will require X. We are converting this to have it in mole per dm cube. This is mole now. We want to get this molar concentration of this in mole per dm cube, but they gave us this volume in cm cube. So we convert it to mole per dm cube. They are saying 25 centimeter cube of it and gave us these moles. So X becomes 1000 times 1.18 times 10 raised power minus 4, at least that is 4, all over 1000 times this divided by 25. So we'll see what that will give us. Times 1000 divided by 25. That will give me 4.72 times 10 raised power minus 3. 4.72 times 10 raised power minus 3. I haven't gotten this. This will now be in mole per dm cube. Now I've established the concentration of Na2CO3 in mole per dm cube. I have the concentration of acid in mole per dm cube. So I will now establish all that I have gotten now. I will now say molar pure concentration of pure Na2CO3 in mole per dm cube is equals to 0.5. We have concentration of in mole per concentration of this in mole per dm cube. Sorry, we have it to be, look at it here, 4 point concentration of Na2, pure Na2 in mole per dm cube. We have it to be this is equals to 4.72 times 10 raised power minus 3. Okay. Then we have concentration of pure Na2 in gram per dm cube. It's going to be this times molar mass. It's going to be 4.72 times 10 raised power minus 3 times 106, which is the molar mass. And that will give me 0.5. That will give me 0.5 gram per dm cube. That will give me 0.5 gram per dm cube. Okay. Now, concentration of pure Na2CO3 is gotten. Concentration of pure Na2CO3 in gram per dm cube is gotten. The next one is for me to get concentration of impure. Concentration of impure now. Remember from the question, they gave us a 30 grams. So it's going to be 30 grams over, the volume is 500 centimeter cube times 1000 over 1. And if we do this properly, we'll be getting 30 over 500 times 1000 is giving us 60 gram. 60 gram per dm cube. So if you watch, what we have got now is concentration of pure Na2CO3 in mole per dm cube. Its concentration in gram per dm cube. Then its concentration of impure, these ones are pure. This one is impure in of this, still in gram per dm cube. Now, having established that, now we can now calculate for percentage mass concentration of impurity. I can clean this. Now I want to calculate for mass concentration of impurity. The mass concentration of impurity becomes mass concentration of impure minus mass concentration of pure. Mass concentration of impure minus mass concentration of pure. So that will give us 60 gram per dm cube minus 0.5 gram per dm cube. And that will produce 60 minus 0.5, 59.5. 59.5 gram per dm cube. Okay, that produces 59.5 gram per dm cube. Okay, now at this junction we have gotten mass concentration of impurity as 50 mass concentration. Then the percentage impurity. Now the next thing is percentage impurity. We are now going to get what we call percentage impurity. Therefore, percentage impurity now, remember it is mass concentration of impurity, which is this, mass concentration of impurity over mass concentration of impure. So, the mass concentration of impure, that is times 100 over 1. This becomes 59.5 gram per dm cube over mass concentration of impure. Mass concentration of impure is 60 over 60 times 100 over 1. So divided by 60 times 100, that is 99.1. That is 99.1%. So we have gotten percentage impurity to be 99.1. What of percentage purity? Though they did not ask that one. It's going to be 100 minus percentage impurity, which is going to be 100 minus 99.1, and that becomes 0.83%. So what we have learned here is that percentage impurity is calculated as mass concentration of impurity over mass concentration of impure. The work here is to calculate for mass concentration of impurity. You see all the steps we went to get mass concentration of impurity. Because for you to get mass concentration of impurity, you need to have mass concentration of impure, which we got mass concentration of impure minus mass concentration of pure. This minus this will give you this. And which is this? We say mass concentration of impurity, which you need, is mass concentration of impure minus mass concentration of pure. And when you do that subtraction, you will have this. The mass concentration of impure, In mass concentration of impure, it is the gram given to you of the salt, which here we have 30, divided by the volume times 1,000 over 1 will give you the value of this, which is what we have here now. So this divided by this times 100 over 1 will give you percentage what? Impurity. So what you need to learn is not to cram it, it's just to learn one thing, how to get mass concentration of impurity. That is to get the mass concentration of impure and mass concentration of pure. Getting the mass concentration of impure is not a problem because the gram of the salt was given and the volume, you get this. But to get these are the problem. To get especially this, you have to start from the acid given, then you have to work your way down to here. So practice how to get to here. Once you have gotten to here, you have gotten this one, your work is done. Because this one, once you have gotten this and you have gotten this minus this will give you mass concentration of impurity, which is this. Then this will take the place of this times 100 over 1 will give you the final answer. So I believe, though it looks too long, but when you practice it, you will get it better. So we go into the next subtopic. The next subtopic we're going into is pH and pOH. You have to have this information that pH is this, pOH is this. pOH is a negative log reading. Hydrogen plus OH minus will give you this. Then pH plus pOH will give you 14. Let's see example number 1. Calculate the pH of the solution, whose hydrogen ion concentration is this. So if H plus is equals to 0.025, therefore pH becomes log to base 10 of 1 over H plus. And that will give me log to base 10, 1 over 0.025. And if you press this in your calculator very well, you have 1.60. So that is the pH of that. So we go to another example. This one says we should calculate the pH of 0.05 molar concentration of HCl. Since they mentioned the acid, we are going to dissociate it. Remember that balance equation for dissociation equation for HCl is a strong acid, so it will give out all hydrogen ion, then chlorine minus. So therefore, 1 mole of HCl produces 1 mole of hydrogen ion concentration. Therefore, 0.05 molar concentration of HCl will also give 0.05 molar concentration of hydrogen ion. So therefore H plus is equal to 0.05. Now pH is now log to base 10 of 1 over 0.05. And if you press that well in your calculator, you are going to have 1.30 as your final answer. I believe that is well understood. Let's go to example. Seeing example 3 on the board, we are calculating for the pH of this. So we are going to first of all dissociate that H2SO4. When you dissociate it, will give you hydrogen, 2 hydrogen plus SO4, 2 minus. So that means 1 mole of this will produce 2 moles of hydrogen. So 0.02 molar concentration will produce 2 times 0.02 molar concentration. That means you are going to multiply this one by 2. And if you do that, you are going to be having it as 0.04 molar concentration. Therefore, hydrogen ion concentration there is 0.04. Then others are history. That pH is log to base 10 of 1 over 0.04, which will give you, if you press it very well, give you 1.40. I believe this is very clear. Let's pick one example from the past question. If you look at this question, 2022 to 2023, question number 5II, it says 1 centimeter cube of 0.2 molar concentration of H2SO4. 1 centimeter cube of this concentration acid is diluted to 100 centimeter cube. 1 centimeter cube of this. Okay, so from that place, once they have mentioned dilution, we're going to use dilution formula. So we'll be using C1V1 equals to C2V2. Okay, so we have that our C1 was given as 0.2. Our V1 was also given as 1 centimeter. Our C2 we don't know, but our V2 was given as 100 centimeter cube. So C2 becomes C1V1 over V2, which we produce 0.2 times 1 over 1000. If you press this well in your calculator, 0 over 100, not 1000, you are going to be having 2 times 10 raised to the minus 3 concentration. So this is the concentration we are looking for. Now remember, we are talking about H2SO4. But if H2SO4 dissociate, it will give 2 hydrogen plus SO4 minus. SO4 2 minus. So if that be the case, 1 mole of this gave 2 moles of this. The concentration of this now is this. So we have 2 times 10 raised to the minus 3 will give 2 times 2 times 10 raised to the minus 3. So that the concentration of hydrogen ion here becomes 4 times 10 raised to the minus 3. Then pH becomes log to base 10, 1 over 4 times 10 raised to the minus 3. And if you do that properly, you will be having 2.4 as a final answer. I believe calculations about pH is well understood. If you have more questions, you can put it in the comment section. Thank you. We move to past question and answers now to look at some questions that we might have not seen. Okay, in this aspect, we'll be looking at the past questions. Okay, so here we have 2020 through 2021. 2020 through 2021. Let's see, it says you are provided with usual apparatus for a titration experiment as well as 50 centimeter cube sample of the following solution: 0.095 molar concentration of HCl, and then disodium triazocarbonate 4. Okay, solution: 6 grams of the impure salt per dm cube of the solution. State how you will perform the following. State how you perform the following. Say A, fill the burette with acid. How will you fill the burette with acid? Okay, if you look at the solution aspect, I answered it as saying the wet burette is first rinsed with a little of acid solution. It is then filled with the acid using the funnel past the 0 mark. Okay, that is how you are going to fill the burette with the acid. Okay, B says how will you transfer 25 centimeter cube of the alkali or alkaline solution into the conical flask? Okay, the answer becomes use a little of the disodium triazocarbonate 4. A little solution of the disodium triazocarbonate 4 is used to rinse the pipette first. So if you want to put for the base, you have to rinse the pipette first. You use the solution you want to use as the base to rinse the pipette first. It's used to rinse the pipette. Then the pipette is then put into a conical flask, and the solution allow into the flask. So you rinse it further, you now pipette it and put into the flask. That is what we are trying to say there. So it says, what indicator will you use for the titration? What color change will you expect? Now, if it was, we have here a weak, this is a solution of a strong acid, HCl, and a weak base, Na2CO3. So the indicator used is methyl orange. Do you observe that? You can check back in your note. The indicator used here is methyl orange. For a strong acid and a weak base, you use methyl orange. Very correct. We have said it in the class there. Okay. It says, if the result of titration with the above solutions are as follows. You have seen the result there. Okay. Okay, we have seen the result there. I don't really know what they want us to do with that result. The question, I don't really know. Okay, number 2. He said differentiate between strong acid and weak base. An acid that completely dissociates in a solution is called an acid, a strong acid. That's an acid that dissociates in water and completely gives us its hydrogen ion concentration is called a strong acid. Complete dissociation in water, that's what we call a strong acid. But a weak acid will dissociate partially. It will not give out all these hydrogen ion concentration. Example of strong acid, we have H2SO4, we have HCl. While example of weak acid, we have CH3COOH. In fact, all organic acids are weak acids. Example, CH3COOH, that's a weak acid. This is a weak acid. Okay, so it will dissociate without giving out all its hydrogen, but others will dissociate and give out all their hydrogen ion. Okay, so the other one is strong alkali and weak alkali. Alkali is base. Now, when we talk about alkali, when they dissociate in water, they give out all their hydrogen ion concentration, OH minus. Anyone that dissociates completely to give out OH minus is a strong base, while the one that dissociates to give partially is a weak base. An example of a weak base, Na2CO3 is a weak base. Example of a strong base, NaOH is a strong base. Okay, just mark that. You can go to search Google for more examples for weak acid, weak base, strong acid, strong base. Okay, we move to question C of that number. I say equivalent point and end point. What's the difference between equivalent point and end point? Now listen, it is written in this book that equivalent point is that point where we have equal volume of acid and base during the titration. When we get to the stage when you are titrating the acid and the base and you are shaking it, there will be a time the amount of acid that has dropped and the amount of base, they are now equal. At that point, we call it equivalent point. Whereas the end point is the point where the color of the titration does what? Change. When the color begins to change, when we say change in the color of the indicator, the color of the indicator begins to change. That is end point. But when the volume of acid becomes equal to the volume of base, that is what we call equivalent point. Please mark that. I think that is well explained here. I think that is okay. Yes, it's well explained here. So that is it. Question number 3 says, write down the acid-base pair which will produce the following salt in neutralization reaction. Acid-base pair. Acid and base that you put together to produce sodium triazole-carbonitrate 5, potassium triazole-nitrate sulfate 6, all those things. So if you see, you will see that they were well explained here. For sodium triazole-nitrate 5, you need to react sodium hydroxide and HNO3, hydrogen triazole-nitrate 5. Then for potassium triazole-carbonate 4, note 6, you are going to use H2SO4 and KOH. Then for sodium ethanoate, you are going to use CH3COOH and NaOH. They are all in this book, the solutions, so you can cram them if you wish to cram them. So that is question number 3. Then question number 4 is using table below, answer the following questions. Then they've given us solutions and they have given us their colors there. B now say explain why the color of the indicator in the sample of rainwater is pale orange, whereas in pure water it is green. We all know that pure water, if once it is pure, it is not acidic. But once it is from rain, it is an acid rain. It is contaminated. So if you put indicator in the pure one, the pH value of that pure one is always 7. So it will be, that's why it gives him pale orange, which is almost like pale orange is almost like which one do we call red, almost like red. Why in pure water it's green? So the color of pure water is green. So that one means that it is neutral. It is neutral. Okay, the answer is there. He said, determine the color of acid, base, and neutral form of each of the following indicator. Question number 5. Okay, so we have that methyl, for methyl orange, for methyl red, we have methyl red. Remember, we have not talked about methyl red. There is methyl orange, there is methyl red, there is methyl green. So for methyl orange, color in water is red. Color in acid is red. While color in water, that is neutral, is red. Color in acid is red, while color in base is yellow. You can see that in the solution part. Phenolphthalein, color, we already saw phenolphthalein. In phenolphthalein, we have color in acid is colorless. Color in base is pink. Color in base is pink. Color in base is pink. Color in acid is colorless, while color in neutral is what? Well, that is water is colorless. Color in water is colorless. Color in base is colorless. Color in base for phenolphthalein is pink, while color in acid is colorless. Okay. What of methyl green? Color in water is green. Color in acid is yellow. And color in base is colorless. So mark about methyl red, methyl orange, methyl green. We have seen methyl red, methyl orange, methyl green. Okay, that ends the 2020-2021. We look at 2021-2022. The first question is talking about calculation. So it says a group of 100 level student chemistry in COOU University, Uli, conducted an acid-base titration to ascertain the concentration of sodium hydroxide. They want to ascertain the concentration of sodium hydroxide. So they fill the burette with 0.3 molar concentration of H2SO4. That means concentration of H2SO4. They gave concentration of the acid there. Concentration of acid is 0.3 molar concentration. Okay. Then acid, tetraoxosulfate 6 acid, standard solution, and used to pipette. Yes, it's a standard solution because its concentration is known. And used acid solution and use pipette to transfer 25 ml of sodium hydroxide. The volume of base is 25 ml. Volume of base is 25 ml to transfer sodium hydroxide. Remember, this one is H of, let us write like this, of H2SO4. Why this one is of sodium hydroxide, like that. Okay. Okay. Now, of sodium hydroxide into 25 ml of this into 250 ml conical flask. Okay. They added 2 drops of methyl orange. Why did we use methyl orange there? Methyl orange has tell us that it is a solution of strong acid and weak base. This is a strong acid, this is a weak base. So they use indicator as methyl orange to the base and titrated with the standard acid solution. Okay, 250 flasks, conical flasks. They added 2 drops of methyl orange to the base and titrated with standard acid solution until a sharp orange color was obtained. Their reading were recorded and reported below. Now, if you watch the reading that was recorded by these children, as they were given as we have the first titer there. We have the first titer. We have first reading here. First reading, let me put it as first. And they have second reading. And they have third reading. They have third reading. In their first reading, they had 22.10 and 0.00. They had 44.60. They had 22.30. They had 22.40. Here they have 0.00. So if we want to get our titer value, we are going to be saying this minus this will give me 22.10. This minus that, 44.6. 44.6 minus 22.3 will give me 22.3. 22.30. 44.6 minus 22.3. Then this will also give me, this one will give me 22.40. Now, if I want to look for the one I'm going to use as my titer, I will do this minus this, 22.1 minus 22.3. Okay, or we'll say 22.3 minus 22.1. It gave me 0.2. You know that we said that it should not be more than, it should not be greater than 0.2. It should not be greater than 0.20 centimeter cube. It should not be more than 0.20. So if you do this minus this minus this, we give you 0.2 is at the point. Okay, this minus this, 22.4 minus 22.3 is give me this minus this will give me 0.1. You see that this minus this minus, what of this minus this? 22.4 minus 22.4 minus 22.1 is 0.3. Okay, 0. This minus this will give me 20. If you do this minus this, it will give me 0.3, which is more than 0.2. So what I'm going to do here is that I'm going to use either this and this or this and this. I cannot use three of them because this minus this is 0.3. It is more than 0.2. So it's either I use this and this, which will give me 0.1, or I use this and this, which will give me 0.2. So I would prefer to use this. So my theta value here will now become 22.4 plus 22.3 divided by 2. My theta value here is 22.35. 22.35 centimeter cube. That is the volume of acid being used. I don't know if you understand what I just did here. So my theta value is this minus this will give me this. I prefer to use, either I can use this minus this. So that is to say 22.30 plus 22.1 divided by 2. That will still give me 22.2 or 22.20 centimeter cube. I can use any of this as my theta value. But I cannot say this plus this plus this divided by 3. Why? Because the difference between this and this is 0.3. This one and this one is 0.3 and it's greater than 0.2. So it's either I use this and this. Difference between this and this gave me 0.2, which is exactly, you say it must not be more than this. This is exactly that. Difference between this and this give me 0.1, which is less than this. So it's either I use this and this, or I use this and this. But I prefer to use this and this because what it gave as 0.1, it gave 0.1, which is far less than this, than giving the one that, using the one that is equal but does not matter. So if I do this plus this divided by 2, it will give me this. If I do this plus this divided by 2, it will give me this. Any of them can serve as my acid value used or my theta value. So that is that. Okay. We move to question 9. So use the information above to answer the following question. Write a balanced equation for the acid-base titration. Okay. I believe this was well explained there in the solution. That is 2021/2022. Let me look for that here. Okay. So please don't mind the solution here that this 3 was used. Please, it's not supposed to be. 3 of them cannot be used. Okay. 3 of them cannot be used. Okay. The balance equation we are seeing there is the H2SO4 plus Na2OH. And that will be, I have plus minus, I have plus minus. This will go for this, while this will go for this. So I have Na2, I have Na2 plus minus plus minus. Okay, I will have Na2SO4. Oh yes, Na2SO4 plus 2H2O. Na2, this plus goes for minus. Why this plus goes to minus? So Na2SO4 having two atoms of sodium, then H2, H2, there is 2 here, there is 1 here, making 3. Okay, we have this, then oxygen, 1 is here, which is from here. Oxygen 1 is here, which is from here. So that is how that one will work out. So that's a balance equation they asked us to find there. Okay, and the now say we should calculate the average titer, which I have done there. Average titer I have done there is going to be this or this. Then the now say we should calculate concentration of sodium hydroxide, that is concentration of this one in mole per dm cube. Concentration of sodium hydroxide in mole per dm cube. Now, if you go back to the question, they gave us okay, let me see, concentration of sodium hydroxide in mole per dm cube. Okay, they've given us, okay, that means we are looking for CB. That is what it will be. Because if you start using CAVA over CBVB equals to NA over NB, you have that CA in mole per dm cube was given. They said that is 0.3. Then VA, volume of acid used. Any of these, let me use 22.35 centimeter cube. Remember, you are going to take it to dm cube. Then we have CB, we don't know. Then volume of base used. Remember, I said that we are using, they said they fill the burette, okay, sodium hydroxide or into it, pipetted 25 ml, 25 ml, okay. Okay, these ones were also in ml, okay. Let me leave this also in ml. Know that 1000 cm cube is equals to 1 dm cube is equals to 1 liter. So if I want to convert these things to dm cube, if you are not comfortable with liter, you can leave it in liter, you can convert to dm cube. So you want to remove m is 1000, so you divide this by 1000. So if I divide 22.35 by 1000, I'm going to be having 0.02235 liters. Okay, so that whatever I'm going to have here, this one also 25 divided by 1000, I will have 0.025 liters or dm cube. So you see that in this case now we'll be looking for CB. So CB here will become CAVANB over VBNA. How do you get NA and NB? If you look at this thing, you see that 1 mole of H2SO4 require 2 moles of Na2OH. So this is NB, while this is Na. So Na is equals to 1, NB is equals to 2. So this becomes Ca 0.3 times Va 0.02235 times Nb 2 all over Vb 0.025 times Na 1. And that should, if you calculate that, you'll be getting the value for, we have 0.3 times 0.02235 times 2 divided by 0.025. And that produces 0.5364 molar concentration. That is a concentration of B in mole per dm cube. That is what it should be there. Then if this say calculate the concentration of acid solution in gram per dm cube, that one we can do very fast because of what we have learned before. Now remember that concentration in mole per dm cube is equals to concentration in gram per dm cube over molar mass. So they asked us to calculate the one in for gram per dm cube now. So concentration in gram per dm cube is equals to molar mass times concentration in mole per dm cube. And the molar mass for, we are talking about calculate concentration of sodium hydroxide solution. So sodium hydroxide in molar mass now is going to be sodium hydroxide. We look for the molar mass of sodium hydroxide and multiply by the concentration. Remember that on a normal, this becomes molar concentration, molar mass, which is for sodium. Calculate the concentration of sodium hydroxide, okay? Sodium hydroxide, the molar mass. So sodium hydroxide molar mass is this. So we can calculate that having 23 plus 16 plus 1 is 40. So that concentration in gram per dm cube will become 40 times concentration in mole per dm cube. That is what we got here to be 0.5364. 0.5364, and that will give me times 0.5364. That becomes 21.456 gram per dm cube. Okay, that ends for that. So we have gotten concentration in gram per. So question number 2 there says differentiate between volumetric and gravimetric method of analysis. Okay, volumetric and gravimetric process of analysis. Here the answer we have, we say that volumetric analysis is that analysis that deals with the determination of the concentration of a solution by simply measuring the volume of that solution that will react with a specific volume of a standard solution. Volumetric analysis, I've explained it in the first time. It is that type of analysis that deals with getting the concentration of a solution by simply measuring the volume of that concentration and finding the amount of it that we finally, let me read it out again. It's an analysis that deals with determining the concentration of a solution by measuring the volume of that solution that you want to determine, and the volume of that solution by measuring the volume of that solution that will be able to react with a specific volume of a standard solution. So that is titration. Gravimetric analysis is that analysis that is meant to determine, that is analysis that determines an analyte. Remember, I've told us what an analyte is. By measuring the mass of the analyte, which will react with a specific volume of standard solution. I think I've explained these two things before. Okay. The question is, explain the term equivalent point and end point. I've said that before. Explain why phenolphthalein indicator cannot be used to distinguish between neutral solution and acidic solution. It is because phenolphthalein indicator appears colorless in acid and neutral solution. Colorless in acid and neutral solution as well. It appears colorless in acid and also in neutral. Okay, we are still in 2021, 2022. Now, it says, explain why phenolphthalein indicator cannot be used in distinguishing between neutral solution and acidic solution. It is simple. It is because phenolphthalein indicator appears colorless in acid and neutral solution. It appears colorless in an acid and neutral solution as well. If you put it in an acid, it will appear no color. You put it in a neutral solution, it will appear no color. So the question says we should explain why phenolphthalein cannot be used to distinguish between neutral solution and acidic solution, because phenolphthalein has the same color in both solutions, and the color is what? Clear solution, as in no color. Okay. Go to question number 3A. What is the pH of the solutions at the end of the following acid-base titration? We have strong base, strong acid. It is in the class I've taught. Strong, just take up that solutions from the class so far. Question number 3B. It says state 6 safety precautions. Please make sure you know this. 6 safety precautions. Then it says list 5 equipment. I believe you should know that. Number 4, explain the following: neutralization reaction, primary standard solution. I think we have said that during the class when I was teaching. So you can go back to the video and see that. It says state 3 personal safety precaution you must observe while diluting a concentrated acid solution. The answer is in this booklet. You can look it up. Differentiate between accuracy and precision. Now, you must know, no matter the answer is here, but let me say something about it. Accuracy is when you are close to the answer, but precision is when you get the exact answer. If answer is 1.5 and you have 1.32, you are close to the answer. That's accurate. But if you have 1.5 direct, then you are precise. That's just the two difference. Okay. Number 4 says explain the following. Okay, we have done that. Number 5, a solution of impure sodium. Now, that one says we should determine percentage impurity. So I want you to study that percentage impurity. Study it very well. Study it very well. It's very simple towards the end. Know the formula for percentage impurity. Then the components that makes it up, know how to get them. They must always give you something about the acid, which from there you get the mole of the acid. From the mole of the acid, that is amount, you have concentration of the acid in mole per dm cube. You have the volume of the acid in cm cube. You convert it to dm cube. Now, the amount of the acid, you now do amount equals to CV. You get the amount of the acid. Then you now write a balance equation. You now say how many moles of the salt or the base will react with the acid. Therefore, X mole, which the mole of this acid you have gotten amount, will give X of the salt. Then you get the mole of the salt. Then the next thing you go back to is the volume of the salt that was pipeted. That volume of the salt, convert it to dm cube. Are you there? Convert it to dm cube, or you do the amount of the salt, the impure salt, like when we did was Na2CO3, divided by the volume in centimeter cube times 1000 over 1. Now you will now get, what you are going to get is the volume, or is the concentration of the pure salt in mole per dm cube. Concentration of the pure salt in mole per dm cube. When you multiply the concentration of the pure salt in mole per dm cube times its molar mass, it will give you concentration of the pure salt in gram per dm cube. So you have gotten concentration of the pure salt in mole per dm cube. You have also gotten concentration of the pure salt in gram per dm cube. The next thing is to calculate the concentration of impurity. And that one is gotten by looking at the mass of the initial salt you use. In that case, we have 30 divided by the volume. In that case, we have 500 centimeter cube. Then when you divide it, 30 divided by 500 centimeter cube times 1000 over 1, converting the centimeter cube to what? dm cube. Whatever you get there becomes the mass concentration of what? The impurity. Now you have gotten mass concentration of impurity. You know, mass concentration of mass concentration of impure. The mass concentration of impure minus mass concentration of pure, both in gram per dm cube, will give you mass concentration of impurity. Then mass concentration of impurity divided by mass concentration of impure times 100 over 1 will give you percentage impurity. I don't know if this explanation went well with you. You can replay it over and over again. Then if you want to calculate the mass concentration of the pure, 100 minus percentage impurity will give you percentage purity. So go back and then see these things and see these things and see this. So when you have it in the exam hall, you don't make mistakes, okay? You are not cramming the figures. There might be mistakes in the figures in pressing calculator, but when you follow the standard, that you get the molar mass, concentration of the acid in mole per dm cube, volume of the acid in dm cube, then the amount, which is N equals to CV, you get the amount of the acid. When you have got the amount of the acid, You balance the equation so that you can get the amount of the what? Salt that also did work there. So by the time you have gotten the amount of the salt, the next thing you move into is to get the amount, as you have gotten the amount of the salt, is to now, the salt, the volume of the salt plus the over the mass of the salt times 1000 over 1 to get the amount of the pure salt in gram per dmq, in mole per dmq. If you multiply mole per dmq times molar mass, you get gram per dmq. So please follow these things. I don't know how to fix that into your head. Okay. Question I say, why is necessary to keep analytic balance in air condition? Let's read that together. Why it is necessary to keep that in is here. Let me be sure it's here. So that, because any slight change in room temperature causes noticeable change in weight of the sample. So you have to put it in air conditioner, because any slight change, it can absorb water from the moisture from the atmosphere. Any slight change can cause an error. So that's just it. So the next one is 2022 to 2020. If you go there, you see that we have already solved all the questions there during the solution. So I believe after studying this exam, this class, take time to study all you have learned about this class. I bet you there is nothing that will come out in the exam that is not what we have said here now. So God help us to remember. Don't forget to subscribe if you have not done so. So that in second semester, we are going to be having a lot of the YDX. We're going to be having a lot of classes on this platform, on this channel, and you'll enjoy your classes from home. Thank you and God bless you.